Welcome to Chapter 4, Introduction to Probability. Chapters 1, 2, and 3, we covered descriptive statistics. Now we're going to get into the basics of probability, which is what you use as the foundation for statistical inference. We'll get into the statistical inference part when we get into chapters 7 through 10 and 12. If you took Math 1630, then you probably already seen some of this before. We're going to cover the basic concepts, the experiment, the different outcomes of the experiment, the concept of sample points, events, how to figure out probability for events. There's three basic ways that you can look at the concept of probability. We're going to cover conditional probability, which is associated with the concept of statistical independence. And then we're going to use a cross-tabulation, sometimes they're referred to as contingency tables, to illustrate some of the basic rules and just generally how to find probabilities. Now, probability is measured on a scale from 0 to 1. If your probability value is close to 0, it means it's not very likely that it's going to occur. When you get on the other end of the scale, when you get close to 1, then it's almost a certain thing that it's going to occur. This is a nice little illustration that shows that scale running from 0 to 1. But as the number gets closer and closer to 1, that is the probability value, it becomes more likely that that event is going to occur. The experiment is the process that generates the outcomes. One of the common examples that's used for teaching probability is to draw one card from a deck of 52 well-shuffled playing cards. The outcome is any one of those cards. That outcome is also referred to as a sample point. The sample space is a set of all possible outcomes. Some examples of experiments are tossing a coin. If it's a fair coin, there are two possible outcomes, either heads or tails, each of which will be equally likely. If you're rolling a die, there's 6 possible outcomes. They're all going to be equally likely unless somebody's done something to make one side heavier than another side to make it different. But in conducting a sales call, you might get a purchase, you might not get a purchase. That's not really a 50-50 proposition. Usually it's much less likely that you're going to get a sale than it is that you're going to miss a sale. Inspecting a part could be defective, might not be defective. It has to do with the proportion of defectives is going to determine those kind of probabilities. But all probabilities have to have a value between 0 and 1. 0 means it's not going to happen. 1 means it's a certain thing. Now the notation, we're using E to represent an experimental outcome, and then the probability of E sub I, where I could be any number, it just depends on the number of possible outcomes, is the probability of that particular outcome. And when you sum it up over all the possible outcomes, it's always going to equal 1. But the probability of the first experimental outcome plus the probability of the second experimental outcome and so forth, when you add it up over every possible outcome, it's always going to equal 1. Now there are 3 methodologies, if you will, for assigning probabilities. The classical method, we assume that every outcome is equally likely. You flip a coin, it's just as likely that you're going to have heads as tails. You roll a die, it's just as likely that you're going to have a 1 as it is that you're going to have a 4. If you draw one card from a deck of 52 cards, any particular card has a probability of 1 over 52. Now the relative frequency method, you look at an experiment or you look at historical data. How many times has that particular outcome occurred in the past? And then you can divide it by the total number of possible outcomes to get the probability. The subjective method, well, we're assuming that all probabilities have to be between 0 and 1. So in your opinion, using your own judgment, what do you think is the likelihood of this particular outcome? As I stated earlier, rolling a die is an example of the classical method. Each one is considered to be equally likely. So you've got a likelihood of 1 over 6 for having a 2. It's the same thing for having a 4. In the Lucas tool rental example, they're looking at past information. They have records for the last 40 days. In the last 40 days, they rented 2 car polishers 18 times. In the last 40 days, they rented 3 car polishers 10 times. You can take the frequency, you can take the number of days and divide it by the 40, the total number, to come up with the probability for a particular outcome. Now in this slide, the probabilities have been calculated. The 4 divided by the 40 gives you a 0.1 probability that on any particular day you're going to rent 0 polishers. Whereas the one that's most common is to rent 2 polishers. That happened 18 times out of 40, and you get a probability of 0.45, 18 divided by 40. With the subjective method, the probability is assigned based upon an opinion. People use their judgment, or they might hire someone else and use somebody else's judgment. But how strongly do you believe that this outcome is going to happen? Then you assign a probability if you think it's going to happen close to 1. If you think it's unlikely it's going to happen, then you're going to assign a probability that's closer to 0. Now the terminology establishes an equivalence between a sample point and a particular experimental outcome. One way to define an event is it's a collection of sample points. Another way to define the event is it's a subset of the sample space. The sample space is composed of all possible experimental outcomes, and you just look at part of those, and that would be an event. The probability of the event is going to be the sum of the probabilities for the sample points that are in that event. So you can calculate the probability just by adding up the probabilities of the individual sample points that comprise that event. But there are other ways to calculate probabilities. There are some basic probability rules that you can use to figure out probabilities. The complement of an event is the opposite of the event, and there are rules that link up the likelihood of the complement to the likelihood of the event. The union of 2 events. Let's say you have 2 events, A and B. A or B is the same thing as the union of A and B. The intersection is the same thing as an AND. A and B is the same thing as the intersection of A and B. Mutually exclusive events are events that don't have anything in common. When you find the probability of their intersection, that probability will be 0. The complement of the event A is everything that is not in A. The textbook uses the notation where there's a superscript of C to represent the complement. It's probably more common to see a letter with a dash across the top of it to indicate the complement. But the textbook uses the superscript C notation to represent the complement. it's always going to be true that the probability of an event plus the probability of the complement of the event is always equal to 1, because that union is the sample space. So you can get the probability of the complement just by taking 1 and subtracting the probability of the event. And that's a fairly useful rule when you're trying to solve for probabilities. If an outcome is in the event A, but it's not in the event B, or if an outcome is in the event B, but it's not in the event A, or if an outcome is shared by the two events, A and B. All of those outcomes are in the union of A and B. Another word for the union is OR. A or B is going to be comprised of all the outcomes that are either in A, or they're in B, or they're in both. The intersection is the same thing as an AND. If an outcome is in both events, if it's in event A and it's also in event B, then that outcome belongs to the intersection of A and B. But all of the outcomes that are common to the two events are in the intersection. But that's what comprises A and B. Now, a union operation is the same thing as an OR. The rule states the probability of A union B, but you can also express it as the probability of A or B. Now let's take an example of this. Let's say that the experiment is that you want to draw one card from a well-shuffled deck of 52 cards. Now in that deck of cards there are 4 queens. In that deck of cards there are 13 hearts. So suppose we want to find the probability that we get a queen or a heart. If you just took the probability of a queen, that would be 4 out of 52. And took the probability of a heart, that would be 13 out of 52. If you just add those two together, you're going to get 17 out of 52. And that's not the right answer, because there's a queen of hearts. The queen of hearts is being counted with the hearts, and the queen of hearts is also being counted with the queens. But it's being counted both places. So at the end of it, you have to subtract the probability of the intersection, which is the AND part. But the correct calculation for that example, using this rule, the probability of a queen would be 4 out of 52, plus the probability of a heart would be 13 out of 52. But the queen of hearts is counted in both places. So you have to subtract the probability of getting the queen of hearts, which is 1 out of 52. And the answer is 16 out of 52. Now that general addition rule covers a situation whether you have events that have things in common or if they don't. But if you have a situation to where the two events don't have any outcomes in common, if they don't overlap each other, they're said to be mutually exclusive. And then you can get the probability of A or B, the probability of A union B, simply by adding the probabilities together. So if you have mutually exclusive events, the probability of A union B is equal to the probability of A plus the probability of B. There's no point in putting in there minus the probability of A and B, because that's going to have a probability of 0. There aren't any outcomes if they're mutually exclusive. Now this slide shows the definition of conditional probability. The definition isn't always the simplest way to calculate conditional probabilities. The vertical bar is read as given. The probability of A given B. But by definition, that's equal to the probability of A intersect, or A and B, divided by the probability of the given event. In this case, that's B. Now this assumes that B is not what's referred to as the null event. The null event has no outcomes. So the probability of the null event is 0, and you can't divide by 0. But the probability of A given B, by definition, is equal to the probability of A and B divided by the probability of B. Now the probability of A given B is equal to the probability of A and B divided by the probability of B. If you take that mathematical expression and multiply both sides times the probability of B, then you come up with the general multiplication rule. The probability of A and B is equal to the probability of A given B times the probability of B. But it doesn't matter in which order you write it. You can write it as the probability of B times the probability of A given B, or you can write it as the probability of A given B times the probability of B. Either way is fine. Now, two events are statistically independent if the occurrence of one of them doesn't affect the likelihood of the other one. So A is statistically independent of B if the occurrence of B doesn't change the probability of A. Now there are three ways that you can determine whether or not two events are statistically independent. If the probability of A given B is equal to the probability of A, then they're independent. But if A is independent of B, then B is going to be independent of A. So it's also going to be true that the probability of B given A is equal to the probability of B. Now if you look at the multiplication rule states that the probability of A and B is equal to the probability of A given B times the probability of B. But if they're independent, you can replace the probability of A given B with the probability of A. And if they're independent, that means that the probability that they both occur is the product of their probabilities. And it makes it really simple to do problems if you have statistical independence, because all you have to do is multiply the probabilities together. But that's a special case. You don't always have statistical independence. But it sure makes life easier when you have statistically independent events. The probability of A and B is just the product of their probabilities. The probability of A intersect B is another way to say it, but it's just the product of their probabilities. I apologize for the shifting of this table. The contents have kind of gone up to where they're not really inside the box. The experiment was to select one of the 75 individuals randomly. The top row that you're not able to read here is FR, SO, JR, SR, and total. It's for freshman, sophomore, junior, and senior. But this group of 75 students have been broken down by their class rank and what their major is. They could have been majoring in economics, information systems, marketing, and then you've got the total. So it shows that there are 15 freshmen, there are 15 sophomores. 30 of the 75 were majoring in information systems. I think the smaller version of this table shows up a little bit better on the subsequent slides. But I'm trying to show you how to work out some of these problems based on this experiment. We're just selecting one out of these 75. That same table's up in the top left-hand corner, but we're selecting one of the 75 individuals. Now, what's the probability that a sophomore majoring in economics is selected? Now, the next slide has the answer to this. but we want a sophomore that's majoring in economics. Now, another way to say that would be that you want an individual that's a sophomore and they're majoring in economics. And when you look at the intersection of sophomore and economics, there are 3 people in that cross classification. So 3 divided by 75 would be the probability. And that works out to be a decimal value of 0.04. Now, what is the probability that an information systems major is not selected? We just do not want an information systems major. The answer is on the next slide. Now, another way to state this was that you want anybody else except the information systems majors. Not is kind of a keyword for the complement. The probability of the complement is equal to 1 minus the probability of the event. So if you want the likelihood that you don't get an information systems major, you take 1 minus the probability that you do get an information systems major. And there are 30 information systems majors out of 75. So 1 minus 30 over 75 will give you the answer. What is the probability that a junior or an information systems major is selected? So it needs to be a junior or it needs to be an information systems major. The next slide has the answer. Now, when you see the word or, you want to think addition. The probability of A union A or B is equal to the probability of A plus the probability of B minus the probability of A and B, or A intersect B. You've got to remember to subtract the part that's in common one time. You counted in A, you counted in B, so you have to take it off once. The probability of a junior or an information systems major. The probability of a junior, there were 20 juniors, so that's 20 out of 75. Plus, probability of an information systems major is 30 out of 75. But out of those 20 juniors, 14 of them were information systems majors. Out of the 30 information systems majors, 14 of them were juniors. So that 14 is getting counted twice. So you have to take it off once. So you subtract the 14 out of 75 to get the answer. Are the 2 events, selecting a sophomore and selecting an economics major, mutually exclusive? Now, what does mutually exclusive mean? Two events are mutually exclusive if they have no outcomes in common. Do we have any people that are sophomores and also economics majors? Well, it turns out there are 3 of those. If you had a cross classification where there was 0 for the entry, then there wouldn't be any outcomes there, and that would mean that those 2 would be mutually exclusive. But here we have 3 sophomores that are majoring in economics, so those 2 events are not mutually exclusive. Are the 2 events, selecting a sophomore and selecting an economics major, statistically independent? Now, statistically independent is not the same thing as mutually exclusive. I want to know if they're statistically independent. How do you determine if 2 events are statistically independent? Well, it turns out that there's 3 ways to do it, and it really doesn't make any difference which one you choose. If one of them works, they're all three going to work. If one of them fails, they're all three going to fail. So they're stated in terms of generic events A and B. So either let A be the sophomore and B be the econ, or vice versa. It doesn't matter. Now I'm going to show one way of determining this, and on this way I'm going to let A be the event that you're selecting a sophomore, and I'm going to let B be the event that you're selecting an economics major. And I'm going to use the first one. I'm going to see whether or not the probability of A given B, the probability of a sophomore given an economics major, is that equal to the probability of a sophomore. If those two numbers turn out to be the same, then that means they're statistically independent. A person being an economics major isn't changing the likelihood that they're a sophomore. So is the probability of A given B, is it equal to the probability of A? Now the probability of a sophomore given an economics, when you say given economics, we're no longer talking about 75 people. When you look up there at the economics row, there's only 25 people that are majoring in economics. We're not talking about any of the rest of them. We're given that this person's majoring in economics, so they've got to be one of the 25. How many of those people that are majoring in economics, how many of them are sophomores? Well, there's only 3. So the conditional probability is 3 divided by 25. That works out to be 0.12, or 12%. Now the question is that probability, that conditional probability, is that equal to the probability of a sophomore? Well, there are 15 sophomores. So the probability of a sophomore is 15 divided by 75, which works out to be 20%. 12% is not equal to 20%, so they are not independent. You could pick the other two ways, either one of them, and it's not going to work out. They won't be equal. But just pick one of the 3 ways and try it. If one of them works, they're all going to work. If one of them fails, they're all going to fail. Well, this concludes the Introduction to Probability, Chapter 4. The attempt at the end of the presentation wasn't to do a whole lot of problems or even to try to do one example of every possible problem. It's just to kind of give you an idea of how you might see this structured when you get ready to take the midterm exam. We still need to work on some more aspects of probability. The next presentation is going to be about discrete probability distributions, and then we'll get into the continuous case when we get into Chapter 6 and we start covering the normal. But I just got to get those ready for you. So we'll be talking again later.